I'm a I'm a structural engineer. I've had a long and enjoyable and very rewarding 50 plus year career as a specialist in the design and construction of post-tension concrete building structures. Um, my career started when I graduated from UCLA in the early 1960s. The first post-tension concrete buildings built in this country were done in the late 50s. So my career covered almost the entire history of post-tension concrete building structures in the United States. And today, I'm going to walk us through what I consider to be the landmarks, the high points in the history of post-tension concrete building construction uh, in this country. Oh, was it that long? 61 years ago, it was the fall of 1963. Oh, I hate this because this tells you how old I am. All you have to do is add those two numbers. This didn't used to be so bad when I was younger, but I think I'm going to change it in the future. I was 23 years old. I had just completed my thesis, my Master of Science in Civil Engineering coursework at UCLA here in Los Angeles. I was almost finished with my thesis. It was close. And I was living on a very meager teaching assistant salary from UCLA. And all of those things considered, it was time to get a job. So, does anybody know what the yellow pages are or were these days? They're, before computers and cell phones, they were a big giant phone book that was kept in virtually every area. They were yellow, the pages were yellow, and they contained virtually every telephone number in that particular area. Anyway, out they came in 1963. And my question was, are there any structural engineering firms that were hiring in the San Fernando Valley, which is where I lived? It's an area north of Los Angeles. A few of the firms were hiring, and amazingly, I got hired by one of them. Their name was T.Y. Lin and Associates. A lot of times we come to a crossroad in our lives and we don't really realize it, which direction we take. The decision to go to work for T.Y. Lin would change my entire life. They were the pioneering firm at that time in pre-stressed concrete, and going to work for Lin for T.Y. started a long, long career as a specialist in post-tension concrete design and construction. It was a really exciting time for post-tension concrete. It had been used in buildings for only a few years, and almost all of those buildings were lift slab buildings, which was very popular at that time. Pre-stressed concrete had just been introduced into the ACI building code, the 1963 ACI code, for the first time. And over the next 50 years, my career spanned every major landmark in the development of post-tension concrete in buildings. It's interesting. A lot of people today don't even know what lift slab construction is, but the American post-tensioning industry owes its existence to lift slab construction. The first lift slab buildings that were built in the United States were built in the mid-1950s, and they used non-pre-stressed rebar slabs. In lift slab construction, it was an interesting type of construction, very popular in the late 50s and 60s. The foundations were built first, of course, then the columns were erected full height. Every column was erected to the full height of the building. The columns were either steel or concrete. Then the slabs were cast in a pile on the ground, one on top of the other. And then each slab was lifted into place by jacks and cables that were attached to the top of the columns. Then the slabs, as each slab was put in position, they were secured to the columns by a variety of different systems of pins and brackets. it was a great system, very, very economical. The cost of the lifting equipment could be amortized over many, many buildings, and it substantially eliminated forming in two-way slab buildings. But there were some problems with the early lift slabs. The problems were deflection and slab weight in the long two-way spans. The slab spans were long, of course, because everybody wanted to minimize the number of columns that were required. So to solve the deflection and weight problems, the lift slab companies changed to post-tension slabs. Post-tensioning was already starting to become used widely in Europe, and the use of post-tensioning was great in lift slab buildings. It reduced the slab weight by about 30%, which really helped on the lifting, and it eliminated dead load deflection, which was really important. Big problem was that there weren't any existing post-tensioning systems in the United States. So each one of the lift slab companies went to Europe for help. Most of the European hardware was for large, grouted, multi-strand tendons in bridges, the Fresnel system and the Manuel system. There was only one European system that was even vaguely feasible for building construction with light, unbonded tendons, and that was a system called the BBRV button-headed tendon system. So we entered into the button-headed tendon era. Each lift slab company returned with a license to market the BBRV button-headed tendon system. Some independent post-tensioning companies like Prescon, Ryerson, American Stress Wire also obtained BBRV licenses to market post-tensioning tendons in the United States. Here's what the button-headed tendon looked like. It was a nightmare. The pre-stressing steel was 1/4 inch diameter, 240 KSI high-strength wires. There was I'll try to illustrate this here. There was a bearing plate that bared directly against the concrete. The wires had cold-formed buttons banged on with a mechanical piece of equipment. These buttons were banged on in the factory. Now, obviously, since that's the case, everything had to be pre-assembled in the factory. The wires, the stressing washer. You can see the stressing washer has a groove in it that was the grip for the jack to grab the stressing washer and stress it. Once the tendons were stressed to the proper elongation, shims were attached. These are the shims were attached, and those held the stressing length in the wires. And the key to this nightmare, there were two important things to notice. Number one, it was completely pre-assembled in the factory. So it had to be, quote, unquote, exact length. Now, that's not precisely correct. If it was a little bit longer than the distance between edge forms, you could wiggle the wires and make up for that. But if it was too short, it had to be sent back to the factory and redone. The other thing, notice that this bearing plate bore directly against the concrete. So there's a bunch of this stuff that sticks out from the face of the bearing plate that had to be covered by concrete. So it required either a formed stressing pocket or an entire pore strip to cover the shims and the hardware that stuck out from the face of the bearing plate. It was a nightmare. It did solve the deflection problems, however, but the tendons created other problems. And as I said, I think I've talked about them. Both the stressing and the dead end anchors had to be attached in the factory. So that meant it required, quote unquote, exact length, almost exact length. If it was a little bit long, you could make up for it. If it was too short, had to go, or you had to change the location of the edge forms. Typically, they were sent back to the plant. It required stressing pockets to cover the shims. And one other thing, whenever intermediate stressing was required, which was in almost every building, I mean, typical stressing lengths were about 80 feet from one end and 160 feet from two ends. And most buildings, most commercial buildings were longer than that. So it required an intermediate stressing joint. And when that was the case, it required bulky and very expensive couplers when intermediate stressing was required. And that happened in almost every building. Everything changed in the early 60s, in 1962. The very first strand post-tensioning system was developed by a man by the name of Edward K. Rice, Ed Rice. He was the president of T.Y. Lin Associates. He was my first boss. T.Y. Lin Associates consulted for precast companies at that time, and T.Y. was also doing quite a bit of post-tensioning work with button-headed tendons, so they knew what the problems were. And all of these precast companies used 7-wire strand for their post-tensioning material. Ed was fascinated with the use of 7-wire strand instead of button-headed 240 KSI wire button-headed tendons. So he developed and introduced the first 7-wire strand post-tensioning system. He couldn't do that under the auspices of T.Y. Lin Associates, so he formed a separate company. It was called Atlas Pre-Stressing Corporation. He formed it in 1962, and it was a company that I went to work for in 1965. It solved all of the problems of the button-headed tendons. It did not require precise length. The tendons could be cut a few feet longer than the concrete length and then trimmed off later after stressing. It did not require formed stressing pockets. It did not require couplers. You just slid on an intermediate anchor to the point of the intermediate joint. Here's a picture of the very first strand wedge anchorage that was used in the United States. It was called a coil anchor. It was kind of a nightmare also. You notice that little thing, that plate, that's not a bearing plate. That was just used to attach the coil to the edge form. The pre-stressing force was held by a coil of high-strength wire that expanded, and the expansion was resisted by the concrete, and that held the wedges, the grippers, in place at the end. And after stressing, the strand was cut off by a torch. I asked Ed once how he got this idea, why he didn't use bearing plates, and it was a kind of a vague answer. He was copying the original Fresnel anchor, which was a very large, high-strength coil, but it also had a bearing plate. Anyway, this was the very first strand wedge anchorage that was ever used in the United States. Since it relied on the tensile strength of concrete, there were many, many breakouts that occurred during stressing, and that was particularly common in lightweight concrete with lower tensile strength, and lightweight concrete was commonly used in Southern California at that time. We used to gather in the late afternoon, and occasionally our field superintendent, Tom Anderson, would come in and be bloodied and torn up from all of the breakouts that occurred during the day with the coil anchorage. Well, we knew we had to replace the coil anchorage with a bearing type anchorage, and we did that in 1963. We did it with a ductile iron casting. It's interesting that very little has changed over the last 60 so years in the anchorage system, but one thing has changed. Here's the basic anchorage over to the left. It was a rectangular shape, so it could be used in thin slabs. Ours was 2 inches by 5.5 inches. It combined the bearing plate with the tapered hole with the wedge, with the hole that anchored the wedges. Now, here's something that might be of interest to those of you who are familiar with post-tension today. We did these castings in multiples. We had a single, we called it the H122. Then we had a double, the H222. Here. It anchored 2 strands. Then we had a triple, the 322. We had a 422 and a 522. The 4s and the 5s were mostly used in beams. But our iron workers just loved these multiples because an anchorage, 5 strands could be anchored at about the same cost as anchoring a single, but it never caught on, and nobody else in the industry has ever used multiple ductile iron castings. Here's what the system looked like. The strand passed through the anchors. The strand was greased and had a plastic sheave, which allowed movement in the unbonded tendon. Here are the grippers, a pair, and we used for forming the little stressing pocket, we used a 2-piece thing that we called a grommet. That went out of style. Now everything is with a 1-piece plastic pocket former. Here's what the anchorage looked like in cross-section detail after it was stressed and burned off. You can see the stressing pocket. This is circular if you looked at it from the end, and it was formed by the grommet. And after the strand was burned off inside the pocket, the pocket was simply filled with grout. We developed small, lightweight, open throat stressing equipment. It was beautiful, very light. You can see the typical jack was the 8.5-inch stroke. It only weighed 39 pounds. A beautiful piece of equipment that has remained largely unchanged over the last 60, 70 years. For a while, after Atlas introduced the strand system, there was a fierce competition between Atlas and all the other button-headed tendon systems. It was Atlas versus everybody else. They called us the negative system because we didn't have a quote-unquote positive anchor. They didn't realize they called us the friction anchorage system, and not realizing that there was nothing that involved friction in the anchorage of the wedge system. It was us versus everybody else. The 3 big companies at that time that I can remember were Preston, Ryerson, and Western Concrete Structures. And after about 7 or 8 years, by the late 1960s, Atlas won the battle of the marketplace. Button-headed tendons became extinct, and virtually all building post-tensioning has been with strand tendons ever since. What happened to lift slabs? That's an interesting question. The lifting companies, in my opinion, made a very serious marketing mistake, which I think led to their downfall. They combined the cost of lifting, and the tendons in their bids. And that meant that independent post-tensioning companies like my company, Atlas Pre-Stressing, we were excluded. We couldn't bid on a lift slab job because there was nothing to compare it with. They included the lifting in their price since they all had tendon systems. What did we do? Well, we formed alliances with what was the emerging flying form industry. At that time, it was just developing. And that, along with joint promotion between post-tensioning companies, flying form companies, and very progressive concrete contractors, allowed us to directly compete with lifted buildings. The total building, we were just a part of a cast-in-place building that was competing with the lift slab buildings. And it turned out that cast-in-place post-tension buildings using large panel flying form systems were very competitive with lifted buildings. And by the late 1960s, cast-in-place buildings became preferred and lift slab buildings became obsolete. I personally think it was short-sighted of the lifting companies to exclude independent post-tensioning companies, even if they owned a post-tensioning company. If they had allowed bidding from independent post-tensioning companies, it's very possible that large panel flying form systems would never been developed or refined to the extent that they are today. And in my opinion, it is highly possible if that had happened If they had allowed if they had allowed competition from post-tensioning, independent post-tensioning companies, and the flying form industry would never have been developed to the extent it is, I think it's possible that lift slab construction would be a significant factor today in medium-rise building construction. Now, there's a caveat to that. There were some very serious accidents with lift slab construction that killed a number of people, and that might have changed that last statement. But in any event, I believe it was a serious marketing mistake on the part of the lift slab companies in excluding us. How much post-tensioning is being done in the United States? It's an interesting question. Based on tonnage statistics that were kept by the Post-Tensioning Institute from 1972 to today, and reasonable estimates before that, going back to the late 50s, I think it's reasonable to state that there are about 5 billion with a B, square feet of building construction in the United States using unbonded post-tensioning tendons. If you assume an average size of about 100,000 square feet, that means that there are about 50,000 post-tension buildings in the United States. Most of those are still in service. And again, that does not include bridges or earth applications. And it's interesting that the largest application in the United States for post-tensioning tendons is residential foundations on expensive soil. They're more than half of all the tonnage that's sold in the United States. So they're bigger than buildings, bridges, everything else. That's a surprising statistic. I think the landmarks, the high points in the history of post-tension buildings in the United States are these. First of all, the introduction of the strand system, obviously, to replace the button-headed tendon system. We've talked about that. The development of the ductile iron casting for single-strand unbonded tendons. We've talked about that. Now, here's one we haven't talked about, the introduction of the load balancing design method, and I'll talk about that in a minute. The introduction of the banded tendon layout for two-way slab systems was enormously important in the history of post-tensioning in the United States. And finally, the formation of the Post-Tensioning Institute. Not finally, but the last one is improvements in corrosion resistance. Corrosion was a big problem in post-tension construction, and I'll talk in a bit about how it was solved. In my opinion, the most important single development in the history of post-tensioning in this country was the introduction of the load balancing or equivalent load design method by TY in 1963. TY wasn't the first person to use it. He didn't invent it, but he did more than any other person to explain it, popularize it, and disseminate information about load balancing. It made the design of pre-stressed concrete about as easy as the design of non-pre-stressed concrete. It was just another load. And it encouraged the selection from among structural engineers of post-tensioning as the preferred structural system. By the way, TY introduced it in a paper that he wrote in the ACI Journal in 1963. Building codes, obviously very important in the history of post-tensioning. Post-tensioning was virtually absent from ACI 3/1871, which contained an interest. There was a statement about the existence of pre-stressed concrete, but the 3/1871 code actually told the designer to ignore secondary moments. That's the only building code requirement that I'm aware of in the history of the world that has ever told designers to violate statics. I joined ACI 318 in 1973. I was a member for just under 40 years, contributed to the writing of many ACI 318 codes. The first code that I was involved in was ACI 31877. The 77 and 83 codes were greatly improved as far as post-tensioning was concerned. They reflected testing that had been done at the universities of Texas and Washington. They addressed the banded tendon distribution for two-way slabs. They, for the first time, had minimum bonded reinforcement requirements, which are very important in unbonded members. And they paid much more attention to indeterminate structures with secondary moments, which did exist. So the 31877 code for the first time recognized the existence of secondary moments. And the codes have continued to improve with much more PT post-tensioning expertise on ACI committees. There were some major construction advances in post-tensioning over the course of my career. Two of them that I like to mention. One was in the area of high-rise construction, and that was developed mainly in Hawaii in the 60s and 70s, and of course the use of banded tendons in two-way post-tension slabs. I took this picture in about 1977 from the top of a high-rise building in a shopping center in Honolulu. Virtually every building, this is in 1977, virtually every high-rise building that you see, or every multi-story building that you see in this picture, was post-tension. Hawaii was a huge initial market for post-tensioning in the late 60s and early 70s. The reason for that is really twofold. One, there wasn't much going on in construction in Southern California at that time, but there was in Hawaii. Hawaii was experiencing a huge input in foreign investment. China and Japan both discovered Hawaii as a very desirable vacation location, and there was a tremendous construction boom because of that in high-rise hotels and condominiums. And again, faster completion meant more revenue, so construction time became the most important factor. Now, in a multi-story building, the vertical elements typically dominate the critical path. You can't build a slab until you have the columns and walls below done. So what's the solution? Build the columns and walls ahead of the floors. And that's what we did. We developed jump forms and flying deck forms. You can see this is a multi-story bearing wall building going up, but the walls and columns are up. Well, it's a bearing wall building, so the walls are up about 3 stories, but there's no slab. So how do you do the slab? You hang it from the walls. We developed a system of holes through the walls through which the rebar and tendons passed. So this allowed the walls to be built ahead of the slabs. And this allowed believe it or not, a 3-day cycle per floor. In a typical Hawaiian multi-story concrete building, the slab concrete would be placed on Monday morning. And remember, the walls and columns are now 2 lifts above. The concrete is in place on Monday. The slab tendons would be stressed on Tuesday morning. And we developed an oversized anchor, 4x6, to permit stressing at 1,500 psi, which was usually achieved in 24 hours. So the tendons are stressed on Tuesday morning. That meant that the flying forms could be pulled and flown on Tuesday afternoon. Then the tendons and rebar in the next floor above would be placed on Wednesday through sleeves in the walls and columns, and the slab concrete in that floor above would be placed on Thursday morning. Monday through Thursday, that's a 3-day cycle. There were hundreds, maybe thousands of floors built that way on a 3-day cycle in Honolulu in the late 60s and 70s. Here are a couple examples of 2 of our buildings, Atlas buildings in Honolulu. The other major construction development that I'd like to address that was really interesting and had a huge influence on post-tension concrete construction, the use of banded tendons and 2-way slabs. It was first used in, brace yourself for this, the most famous post-tension concrete building that was ever built. What do you think that was? It's the Watergate Apartments in Washington, D.C. Yep, the very same one that you're thinking of. It was built in 1968, and its fame came not so much from the fact that it was post-tension, but for what happened in it during the Nixon regime. The Watergate apartments were an extremely complicated building. They were curved. Um, they're. Let me see if I skipped the slide. No, I didn't. The layout was extremely complicated. Um, at that time, the typical system used for two-way post-tension slabs, is what was called the basket weave system, where some of the tendons were placed in narrow imaginary strips over the columns, and some were placed in what were called middle strips between the columns. The tendons were draped in a curved vertical profile, which was high at the column lines, low at midspans, and a single tendon profile had some orthogonal tendons above it and some below it. So this is what a profile looked like. One single profile of a number 2 tendon had some tendons below it, number 1, and some tendons above it, number 3. That meant that the detailer had to find the single tendon first, which was below every other tendon. And that was sequence number 1. That got placed first. Then he or she had to find the tendon in the other direction, perpendicular direction, which was below all the remaining tendons. And that was tendon sequence number 2. A typical slab would have 30 to 40 sequence numbers, and the ironworkers had to place the tendons in exactly that sequence, or you'd end up with a bird nest. Here's what a basket weave tendon slab looked like. This is a foundation map, but it exemplifies the basket weave system. The tendon with the arrow to it. Let me see if I can find it. Yeah, this tendon goes under this tendon and over this tendon. So it had to be placed exactly in that sequence. And this is what the basket weave tendon, what a basket weave slab, a foundation mat in this particular case, what it looked like. Very complicated. And again, any errors in the placing sequence resulted in a bird's nest. You couldn't share the tendons. Let's go back to Watergate, 1968, excuse me. In Watergate, the columns didn't line up in either direction. It was extremely complicated, curved slabs. The spans were short, just 22 feet maximum between columns, but the columns were located, the architect located the columns where they could be hidden with no regard to a grid system, either in closets or some type of superstructure. Again, the building was curved. There were no grid lines. The column locations were actually identified by coordinates. The concept of column strips and middle strips was meaningless and the load path was virtually impossible to follow. The structural engineers for the slab was a combined effort of T.Y. Linen Associates and Atlas Prestressing Corporation. And someone in the design team, it wasn't me, I was there, but it wasn't me. Somebody said, hey, I've got an idea. Let's think of this slab as a one-way slab. Let's assume that there's a line connecting the columns in one direction, and that's the beam, and we'll consider that a beam. And all of the tendons in the orthogonal direction are like a one-way slab, uniformly distributed. Now, the load path was easy to follow, like in a one-way beam and slab system. And believe it or not, it worked. And it resulted in a significant savings, a bonus, a savings in labor costs. It eliminated tendon sequencing. All the band tendons are installed first, of course. Then all the uniform tendons are installed next. There's only 2 sequence numbers. And of course, the banded system has become the standard method for tendon layout in two-way slabs now for more than 40 years. There are hundreds of millions of square feet in service. The behavior has been studied and verified in numerous laboratory tests. Here's one of those early tests. This is a 4-panel test of a banded slab at the University of Texas at Austin. The banded layout is fabulous. This is an example of a very simple, light tendon layout with the band running up and down and the uniform tendons running left to right. This is a simple but heavy banded tendon layout, still simple. Here's a complicated tendon layout with the bands, and the banded tendon system is magnificent for complicated layouts because it allows an easy way to see what the load path is. No discussion of the history of post-tensioning would be complete without a discussion of the use of computers in post-tension concrete design. When I graduated from UCLA in 1963, and I started my first job as a structural designer with T.Y. Lin and Associates, this was my primary mathematical tool. Well, a lot of you probably have never seen one of these or even heard of it, but it's called a slide rule. It could multiply and divide, but it didn't know where the decimal point was. I had to figure out where the decimal point was. It gave me the right numbers, but I had to figure out what the decimal point was. Now, I can do a dynamic analysis of a 40-story building on a 1-hour flight between San Francisco and Los Angeles on a laptop computer about the size of a book. Oh, I shouldn't say that. I could while sipping a glass of Cabernet. I never do that. I wouldn't do it. Most likely it'd be Shiraz. And all the decimal points would be in the right place. Just in one lifetime, the changes in computing power have been astonishing. From slide rules to personal computers the size of a notebook. And they've got more power than mainframes that took up an entire air-conditioned large room. I said in this building because I've given this talk at UCLA many times. Let's look at my personal journey through this whirlwind of technology. This was my first introduction to machine calculations in post-tension concrete. It was called the Olivetti Programma 101. It came out in 1966. It was just a giant hand calculator. The output was printed on a roll of calc paper here, and the program steps were recorded on magnetic tape strips. It was really just a very large calculator. But it did show the power of machine-assisted calculations. It was machine language. You'd enter a number, arrow up into another space, divide or multiply, store the answer someplace, and it would record the program steps on magnetic strips, like a macro. The input and output were printed on a roll of calculator paper, single column strips. Then the output strips were trimmed and taped to pre-printed calculation sheets. And I'll show you what they look like. For a short time in the 60s, scissors became a primary structural design tool. Here's what our Atlas calc sheets look like. The pre-printed variable titles in the upper left-hand corner shows you that for the loads, beams and slabs, the beam properties, and then we would trim the output from the strips to the right size and glue them on right next to the input sheets. And I had the audacity to call this a computer example, which I guess in a kind of a funny way it was, but notice that the date is 1972 for these. Then along came a fantastic period in the development of computers, the Wang 700 series. Really the first real computer. It wasn't a real computer yet. It was a super calculator. It didn't have a language. It had machine language only. You recorded the program on audio cassette tapes. They were read-only. It had much more capacity than the Olivetti, more registers, more places to store stuff, and you could print with a modified IBM typewriter. It wasn't a design program. You input a first guess at geometry, force, and profile. It performs an analysis, and if you're not happy with that analysis, you change something and start over and iterate to an acceptable design. The moments and shears were calculated with two-cycle moment distribution, either done by hand or with a programmed routine. There was no possibility for matrix inversion. Here's the first real personal computer. It was the Wang 2200, which was introduced in 1973. It had a basic interpreter. It had a basic language. You could do loops, make decisions. It had a mighty 4 kilobytes of RAM. So you can see that required some really heavy-duty programming. You'd input some data, do some calcs, print the answers with a selectric typewriter, delete the unneeded data, input some more data, do some more calcs, and eventually you got to an answer that you liked. The program code was recorded on audio cassette, read-only. The output was printed on 8.5 by 11 sheets with a modified selectric typewriter. For the first time, you could use a tabular format with alpha headings, and all subsequent programming became easier. If you could program the Wang 2200 with 4 kilobytes of RAM, you could program anything. And then the world changed in 1981 when IBM introduced the first personal computer. It was called the IBM Personal Computer. The PC had 2 floppy disk drives. You could read and write. Had a dot matrix printer that you could print directly to. It had a huge 64 kilobytes of RAM. It had a mighty processor speed of 4.77 megahertz. It had no hard drive, and it did have a basic programming language. In 1983, IBM introduced the XT, which was a personal computer that had a floppy drive for the first time. The XT was the first personal computer with a built-in hard drive, mighty 10 megabytes, had 128 kilobytes of RAM, and the same processor speed of 4.77 megahertz. It allowed huge improvements in post-tensioning programming. We could now do matrix methods. You could do true design programs with iteration within the program, had much more sophisticated routines like the one for punching shear that we developed. And you didn't have to spend so much time juggling and printing data. You could actually do refined calculations with the XT. Then again, the world changed in a big way in 1985 with the introduction of Windows. It replaced DOS as the prevalent operating system. It was originally a 16-bit system with a system called Visual Basic in 1985. It allowed third-party programmers to use all of the beautiful Windows fancy interfaces and I/O routines. It changed to a 32-bit system in 1994. That required major conversion for 16-bit programs, caused us a lot of headaches. And it changed again to a 64-bit system in 2009 with Windows 7. And it changed its language to Visual Basic Net, which required another major conversion for 32-bit programs. Windows is amazing. The growth in Windows is astonishing. Since the first personal computer, RAM has introduced 60,000 times. The processor speed has increased 300 times, and the disk storage, which is still increased, has increased at least 100,000 times. Amazing increase in computer power. There were problems with post-tensioning. 2 major ones I could cite. The first one was restraint to shortening. The mechanics of restraint to shortening is different in pre-stressed and non-pre-stressed members, and engineers had to learn how to design post-tension floor systems with levels of cracking that are normally accepted in non-pre-stressed systems. And those methods included physical systems like joinery details and non-pre-stressed reinforcement. The biggest problem that we ever faced in post-tensioning was tendon corrosion. The early sheathing and grease were inadequate for aggressive corrosion environments like in the Midwest where de-icing salts were placed on the top slab. Material specifications developed by the Post-Tensioning Institute have largely solved the early corrosion problems. The improvements in sheathing material and coating, and in the worst cases, complete encapsulation, which is required in every tendon, have really solved the corrosion problems. What do I see as the future in post-tension concrete? I see 2 things that I'm sure will happen. They're happening now. One is the strengthening of existing buildings with externally applied post-tensioning tendons. This is a very green concept. It involves retrofit of existing buildings versus replacement. So it's very compatible with the extended useful life that is important in sustainability of buildings. And the second thing that I see in the future of post-tensioning is the use in tall concrete buildings. Here's what the typical plan of an external tendon strengthening system looks like in post-tensioning. I don't see my pointer, but anyway, it's a harped tendon system that's built underneath the existing slab or beam. On the left column, a hole is drilled. Well, a hole is drilled through every column for the tendons to pass through. A bearing plate is on the two external sides. The tendons pass under a structural steel tube that we call a saddle. That applies a force to the bottom of the slab just at the point where you want it, and it's anchored somewhere on the right. Here's what it actually looks like in the field. This is an actual two-way slab with a load at mid-panel. That white stuff is the fireproofing. The fireproofing, if it's required, and it isn't required in a lot of buildings that we've done, it's a vermiculite plaster that's applied to a self-furring metal lath that's wrapped around the tendons. The other major factor that I see in the future of post-tensioning is in tall buildings. There's a historic perception that all tall buildings must be built with structural steel. That's changed. High-strength concrete now makes the column sizes reasonable, and post-tensioning reduces the weight of the floor systems by about 30%. And this results in savings in all load-carrying members, the columns, the foundations, and the seismic or wind system. The advantages of post-tensioning in tall buildings is cost, of course. That's always the most important advantage. The cost of the floor system itself, the reinforcing, the reduced height and volume of the building, and the exposed, it allows the exterior frame, beams and columns to be exposed, which saves a lot of expensive curtain wall. It has advantages in fire and blast resistance, catastrophic loads. Concrete is inherently fire resistant. As I said, it allows you to expose the exterior beams and columns. There's no vertical path for fire from floor to floor, and that results in a substantial savings in curtain wall, usually about 25%. And there are advantages in sound and vibration. Two tall buildings that I was involved in that I'd like to cite, well, one of them, is a building in Burbank, California, called 3900 Alameda, the tower. At the time it was built, late 1980s, it was the tallest concrete building ever built in what was called seismic zone 4. And again, it was built in, I think it was completed in 1988. There is an article about this building in the Journal of the Post-Tensioning Institute. It's 32 stories. It's completely cast in place, has a 7-inch thick post-tension flat plate floor system, has monolithic cast-in-place downturn perimeter ductile moment frames. Most of the frame beams and columns are exposed at the perimeter. That replaced about 25% of the exterior curtain wall. And of course, it has much improved fire resistance between floors. The other important high-rise concrete building, which is post-tension, is a building in San Francisco at 3rd and Mission called the Paramount Apartments. Was completed in 2002. It's 43 stories tall. It still may be the tallest concrete building in what's called now seismic design category D, E, or F. It was the first post-tension precast concrete moment frame building that was ever built in that highest seismic zone 4. It involves the first use of unbonded post-tensioning as the primary reinforcement in the moment-resistant frame beams. It has a two-way post-tension flat plate floor system, which minimizes dead load and reduces vertical and lateral loads. And it also, by the way, has a thick, I think it's 8 feet thick, post-tension mat foundation. This is an exciting time for having a career in post-tensioning. It always has been. in the early days, we saw the history of post-tensioning becoming a trend. Um, I think that expertise in post-tensioning will be in great demand for 2 or 3 more generations. And again, this is primarily aimed at students where I give the lecture often, but for all of you, have a lot of success and much fun in your careers. And that's it. I see some questions. First question is, do I understand correctly that the post-tensioning companies did not have capacity to lift the slab? That's correct. There were the existing lift slab companies all had post-tensioning tendon capability, but none of the independent post-tensioning companies had any capability to do the lifting. The next question from Jesus is, what were the tensioning sequence on basket weave tendon layout? Typically, the uniform tendons, that's an interesting question. There was no significant sequence involved in a basket weave tendon layout. No, you don't still have a slide rule. That's impossible. I don't think I have one. Here's a question. I have worked on some buildings in Honolulu that made use of paper sheath tendons. You mentioned that plastic sheaths and grease were used very early in the development of PT. What was the purpose of using paper sheathing in the first place, and when did they realize it wasn't going to be viable long term? Good question. The early buildings, much of the early post-tension building construction in Hawaii was done by Atlas Prestructuring Corporation, my firm, and we used paper sheath tendons at that time. We didn't switch to plastic until the mid-70s. Okay. You said there might be some more questions. Oh yeah, here's one. Picking up on your slide regarding concrete being inherently fire resistant, do you have an opinion on whether end spans of post-tensioning slabs should be considered restrained or unrestrained? Well, the Uniform Building Code kind of solves that by requiring that they be considered unrestrained. So we follow the Uniform Building Code and consider end spans to be unrestrained and use a little bit more fire cover in end spans. From Hartanto, what do you think is the difference between post-tensioning practice here in the U.S. versus the rest of the world? Well, much more widely used in the United States than probably anywhere else, although it is widely used in other countries. It isn't as extensively used as in the U.S. And I'd say there are many more applications of bonded tendons being used in other parts of the U.S. than in this country. Almost all of our building construction has been unbonded, and that's kind of unusual. The last question that I see is, what about waffle slabs? We've done an awful lot of them. I like them. I think they're a very efficient method of construction. They minimize the amount of concrete. They minimize the amount of post-tensioning. I think they're very efficient. The cost of the waffle forms are usually relatively insignificant. So I like them very much, but you don't see them very often. You know, they're much deeper, of course, than a solid thickness slab. But I have always liked the use of waffle slabs. Well, we're just at about the hour. I see 11:59. Any other questions? Okay. Yeah. There. I see it. Okay. Yalina, with the amount of conduits being added to post-tension decks, do you have any advice on the placement of the conduits as they relate to the tendons? Current code only requires to maintain clear cover. So largely a decision on the spot. I mean, obviously, you don't want them close. Um, it's a common sense decision, Yelena. I agree that there's some of the two-way slabs that we see have enormous amounts of conduit, but as long and the banded tendon system has really helped that because you can run the conduit parallel to really both to the bands and the uniform tendons. So it's largely a matter of judgment in the inspection of the final placement. We've had, maybe it's because of the quality of inspection, but we've had very, very little, in my career, we've had very, very few problems with breakouts due to conduit. And the last question I see is, when finding the effective length factor of a column bounded by flat plates, top and bottom, do you think we should consider the width of the column strip to compute the moment of inertia of the beam? Yes. Thank you. Thanks, everybody.